UDP User Datagram Protocol, is a fast, connectionless, and lightweight Internet protocol characterized by unreliable, best effort delivery, meaning it sends data without guaranteeing arrival, order, or duplication prevention, ideal for time-sensitive apps like streaming and gaming where speed trumps perfect accuracy. Its key traits are minimal overhead, small 8-byte header, no connection setup, lack of flow/congestion control, and support for broadcast/multicast, contrasting with TCP's reliability. Core characteristics: connectionless, no handshake needed, datagrams, are sent immediately. Unreliable delivery, no guarantee packets arrive in order, or arrive only once. Low latency/high speed, faster due to minimal processing and overhead. Lightweight, small 8-byte header, ports, length, checksum. Stateless, no session information maintained between sender/receiver. No flow control, can overwhelm receivers or networks. No congestion control, sends data regardless of network conditions. Supports multicast/broadcast, efficiently sends to groups or all network devices. Typical applications: due to its low latency, UDP is ideal for time-sensitive tasks where missing a few packets is preferable to waiting for retransmissions, real-time media, VoIP, video conferencing, and live streaming. Online gaming, rapid state updates where current data is more important than old, retransmitted data. Network services, DNS, Domain Name System, DHCP, and NTP, Network Time Protocol. A UDP, User Datagram Protocol, packet, formerly known as a datagram, consists of a fixed 8-byte header followed by the actual data, payload. Its structure is designed for simplicity to minimize processing time and overhead. UDP packet structure: field size description 16 bits, 2 identifies the sending application's port. It can be set to 0 if no source port bytes, response is needed. Destination 16 bits, 2 identifies the receiving application's port on the target device. Port bytes, 16 bits, 2 specifies the total length of the datagram in bytes, header plus payload. Length bytes, the minimum value is 8 bytes. 16 bits, 2 used for basic error checking of the header and data. It is optional in checksum bytes, IPv4 but mandatory in IPv6. The actual information being transmitted, example streaming video frames data, payload, variable or DNS queries. Key technical details: total header size, fixed at 8 bytes, compared to TCP's variable 20 to 60-byte header. Maximum payload size: theoretically, the maximum size of a UDP datagram is 65,535 bytes, including the header. However, the practical limit is often smaller, typically 65,507 bytes, due to underlying IPv4 header requirements and network MTU, maximum transmission unit, limits. Checksum calculation: to increase accuracy, UDP uses a pseudo-header, which includes source and destination IP addresses, during the checksum calculation process, though the pseudo-header is not actually transmitted with the packet. No sequencing: unlike TCP, the UDP header contains no sequence numbers. If packets arrive out of order, the application layer must handle reordering. In a DNS query sent over UDP, the 8-byte UDP header wraps the DNS payload to ensure it reaches the correct service. Below is a breakdown of an example UDP header for a standard DNS query. Example: a client asking for google.com. Example: DNS query UDP header. Suppose a client uses a random high-numbered port to send a query to a DNS server at port 53. Field size: example value, decimal, hexadecimal representation. Source port 2 bytes 52110, ephemeral port, 0xCB8E. Destination port 2 bytes 53, standard DNS port, 0x0035. Length 2 bytes 40 bytes, header plus payload, 0x0028. Checksum 2 bytes, variable, 0x1A2B. When a UDP datagram is sent over a network, it is encapsulated within an IP packet. This means the entire UDP segment, header plus data, becomes the payload of the IP packet. Visual representation of encapsulation at the network layer: the IP header is wrapped around a UDP datagram, IP header, 20 plus bytes, UDP header, 8 bytes, added at network layer, added at transport layer. Field by field: example, IPv4. If a computer sends a 32-byte DNS query from port 52110 to a server at 8.8.8.8, the final encapsulated packet looks like this: 1 IPv4 header, minimum 20 bytes. The IP header contains instructions for routers to move the packet between networks. Version 4 for IPv4. Protocol 17. This is the critical field. A value of 17 tells the receiving computer that the payload inside is a UDP datagram. Source IP: example 192.168.1.5, the sender's address. Destination IP: example 8.8.8.8, the DNS server's address. Total length, 60 bytes, 20 bytes IP header plus 8 bytes UDP header plus 32 bytes data. 2 UDP header, fixed 8 bytes, nested directly after the IP header, it handles the delivery to the specific application. Source port, 52110, the client's return port. Destination port, 53, the DNS service port. Length, 40 bytes, 8 bytes UDP header plus 32 bytes data. Checksum, used to verify that the UDP data and header arrived intact. 3 data, payload, DNS query, the actual 32-byte message containing the request for a domain name. Summary of the process 1. Transport layer, the application generates data, UDP adds an 8-byte header to create a datagram. 2 network layer, IP takes that datagram and adds its own 20-byte header, creating an IP packet. 3 data link layer, the IP packet is then typically encapsulated into an Ethernet frame, adding a MAC address header, for physical transmission. UDP is commonly used for time-sensitive or lightweight networking tasks where speed and low overhead are prioritized over perfect reliability. Common UDP applications and destination ports. Application/service destination port, S, primary purpose DNS, domain name 53 translates domain names into IP addresses. System, DHCP, dynamic host automatically assigns IP addresses to 67, server, 68, client, configuration, devices on a network. Lightweight file transfer, often used to boot TFTP, trivial FTP, 69 diskless workstations. NTP, network time synchronizes system clocks across a 123 protocol network. SNMP, network monitors and manages network devices like 161, agents, 162, traps, management, routers and switches. Collects and stores log files from various syslog 514 network devices. Used for signaling and controlling VoIP/SIP, voice over IP, 5060 voice/video communication sessions. 500, ISICMP, 4500, NAT facilitates secure encrypted tunnels for VPN, IPsec/L2TP, T, 1701, L2TP, remote access. MDNS/SSDP 5353, MDNS, 1900, SSDP, local device discovery and name resolution default port for one of the most open VPN 1194 common VPN protocols. Remote authentication and accounting radius 1812, auth, 1813, ACCT, for network access. Dynamic and unassigned port use cases. Many modern high-bandwidth applications use UDP but do not rely on a single well-known port. Online gaming uses varying port ranges, often 49,152 to 65,535, for fast state updates. Video streaming, services like YouTube Live or Twitch often use the real-time transport protocol, RTP, over dynamic ports to minimize lag. HTTP/3, quick. The latest web protocol version runs over UDP, typically port 443, to speed up web page loading. The UDP checksum is calculated using a 16-bit ones complement sum of a combination of the packet's data, its own header, and a pseudo-header derived from the IP layer. This process ensures the packet has not been corrupted or misrouted during transmission. The 3 components of the sum before calculation, the following 3 parts are concatenated. 1 pseudo-header, to ensure the packet reached the correct destination, UDP includes critical fields from the IP header. IPv4 pseudo-header, source IP, destination IP, reserved, all zeros, protocol, 17 for UDP, and the UDP length. IPv6 pseudo-header, source/destination IPv6 addresses, UDP length and next header, 17. 2 UDP header, all fields, source port, destination port, length, except the checksum field itself, which is temporarily set to 0. 3 payload, data, the actual application data being sent. If the data has an odd number of bytes, a 0 padding byte is added to make it divisible into 16-bit words. Step-by-step calculation, sender, 1. Divide into 16-bit words, treat the concatenated pseudo-header, header, and data as a sequence of 16-bit integers. 2. Sum the words, add all 16-bit words together. 3. Handle carryover, if the sum exceeds 16 bits, producing a carryout bit, that carry bit is wrapped around and added back to the least significant bit of the sum. 4. Final inversion, take the ones complement of the final sum, flip all bits, 0 becomes 1, and 1 becomes 0. 5. Insert checksum, place this final 16-bit value into the UDP checksum field. Note, if the calculated result is all zeros, it is sent as all ones, 0xFFFF, because a value of 0x0000 in the field indicates no checksum was performed. Verification at the receiver performs the same sum over the pseudo header, UDP header, data, and the received checksum itself. Result 0xFFFF, all ones the packet is considered error-free. Any other result, an error has been detected, and the receiver typically discards the packet. TCP, Transmission Control Protocol, and UDP, User Datagram Protocol, are the two primary transport layer protocols used for Internet communication, each optimized for either reliability or speed. Key differences comparison, 2025, feature TCP, Transmission Control Protocol, UDP, User Datagram Protocol, connection-oriented, requires a connectionless, sense data type handshake before data exchange. Immediately without a formal session. Guaranteed, tracks packets, checks for best effort, unreliable, lost or reliability errors, and resends lost data. Corrupted packets are not retransmitted. Ordered, delivers packets in the exact unordered, packets may arrive and be data ordering sequence they were sent. Processed in any order. Variable, 20 to 60 bytes large due to fixed, 8 bytes minimal overhead for header size extensive control information maximum efficiency. Slower, high latency due to connection faster, low latency, optimized for real speed setup and retransmissions. Time applications. Congestion yes, slows down data rates automatically no, continues sending at the same rate control if the network is busy. Regardless of network state. Not supported, strictly one-to-one supports both broadcast and multicast broadcasting communication. To multiple recipients. Practical applications use TCP when accuracy is critical, ideal for web browsing, HTTP/HTTPS, email, SMTP/IMAP, file transfers, FTP/SSH, and banking transactions where missing data could cause errors. Use UDP when speed is critical, ideal for online gaming, low latency state updates, video conferencing, Zoom/Teams, live streaming, and network services like DNS or DHCP. Modern trends in 2025. Many modern services now use hybrid approaches. For example, platforms like YouTube and Netflix often use the QUIC protocol, built on top of UDP, which provides the speed of UDP while building TCP-like reliability and security into the application layer for faster web page and video loading.